Hi there. My name is Kyle Sword. I'm the manager of business development for NSG Pilkington in North America. And today I'm going to be talking to you about glass options for enhanced building design. So this is an AIA accredited course. So if you do need continuing education credits, I can get you credits for that. Just let me know if you after you attend. But what I'm going to talk today is about different types of glass. So these are typically high performance glass products that get used in buildings, commercial and residential. And I'll also talk about some specialty applications within that space. I'm going to talk a little bit about design potential, how some of these ideas can impact your design. I'll talk about emerging technologies. These are sometimes new products. Sometimes these are things that are kind of coming. And sometimes there are ones that are just available and have been for a while, but people just don't have much awareness on how to use it. And then lastly, I'll talk to you about green and sustainable policies. So this is a course that typically I give architects. A lot of times I do it at different trade shows and conferences, but I also do this in internal meetings. I do it with students. I do a wide variety. So I try to cover a pretty broad base. So the first thing I'll talk to you about glass and glazing overview. And we are a glass company. We have around the world around 27,000 employees. We make flat glass through the float process in about 30 some countries. We really make large sheets of glass. And we've been in this space for almost 200 years. And really the last 50 years, I tell people, glass and windows has become exceedingly complicated. So back to about the 1970s, what you see here on the left is our company in North America was called Libby Owens Ford. So we at that time were one of two manufacturers in North America. And essentially, we made 13 products. What you see on the left is our full catalog of all the products that we made and all the performance. In the middle here, this is our sample kit. This is what we'd send to customers. We had 4 colors, maybe 3 or 4 different thicknesses in those, about 13 products, and you would cut that into a rectangle, you'd stick it in a frame, and that was how you made windows for commercial and residential buildings. Compare that to today, people make what's called IGUs, or insulated glazing units. So typically that's 2 pieces of glass with at least some type of low E coating on the inside surface, and it could be a couple different ones. This is one of our customers in North America, and that's a 2-page catalog of just the alternatives that they offer in terms of double glazed units. So now there's maybe 24 different manufacturers of low E coatings and different levels of low E coatings. There's sputtered and hard coat, and you have some that are forced surface low E's, and this doesn't even add in the complexity of added function. This is just performance ones. So windows and glass have become very, very complicated. But when we make glass, we're making this in what's called the float process. This was innovated in the 1950s. And essentially what we do is in a very, very large furnace. It's like about a 7,000 square foot ranch house. So single story that is filled 4 feet deep with molten glass. That's the sort of scale that we have in our float lines. Very, very large industrial manufacturing. We take sand, soda ash, dolomite, we dump them in together, and you melt that in this major furnace. And if we want to change the color of the glass, we do it at this point with the raw materials. This is from a clear, a low iron, a green, a blue, that sort of thing. It's all done at this process. So we melt the glass, we float it onto a bed of liquid tin. That liquid tin makes the glass very, very optically clear and very flat. You cool it from about 2,000 degrees down to about 1,000 degrees, put it on a roller bed, cool it down to room temperature, cut it up into big rectangles, and then you use that to laminate, temper, that sort of thing. So we do a variety of things there. When I talk to architects, though, typically what I'm talking about in terms of performance boils down to about 3 main things. So when we talk to people, we're talking about, when I look at this window, how does it perform? Well, what's the daylight? How much daylight do I get through? How much of the visible light transmission do I get? So between 0 and 1, 1 is 100% of the daylight gets into the room, 0 is blackout blinds. U factor, how good of a window is an insulator is the window. So, typical walls might be like an R20 and R30, very, very highly insulated. And when we talk U factor, that's the inverse of our value in North America. So a typical window is a U.25. And in the UK, I think that would be like a 1.4 watt per meter square, something like that. So anyway, how good of an insulator is the window? And SHGC, how much does that window or glass reduce the solar load that comes through the window? So, 1 being 100% of the sun's energy comes into the building, and 0 means it blocks out all the heat from comes in. But those are the things that we typically talk about. And I tell people 2 things. One is there's no magic glass. The physics behind this says you can't have a window that's 100% visible daylight and it doesn't let any of the heat. It just doesn't work that way. So there's no free lunch. There's definitely trade-offs in terms of all these different things. But with that said, the other thing I say is you can take a snapshot in time, a 0.3 SHGC, a 0.3 U factor, and a 70% daylight, and I can probably give you a dozen different combinations that'll hit those performance values, but they will look dramatically different. So it's not just how does it perform, you also need to know what you're trying to accomplish in terms of the aesthetics. And there's really two things that we're trying to do with glass and windows and coatings. And again, oversimplified, but what we're trying to do is use that as a filter. So if I look at the bottom right here, this is the solar spectrum. So the sun's energy comes in as UV, visible daylight, and near IR. And if we could make a perfect coating, which we have some pretty good ones, what we would want to do is knock out all the UV, let in a lot of visible daylight, and knock out all the near IR. So if I do that, you can see that about 40% of the energy comes in with visible daylight. So you're going to get about a 0.4 SHGC if you have a very, very high daylight product. If you want something that's lower than a 0.4 SHGC, you have to take out a little bit of the sunlight. That's just the nature behind it. So some coatings do a better job of this than others, but that's mostly what we're trying to do with coatings and glass. The other thing we're trying to do is we're trying to make the windows into better insulators. So that's done several different ways. You have an air pocket or an argon pocket, some sort of gas in between. You have different sort of coatings that perform better than others. But essentially what we're trying to do with that whole makeup is the sun's energy and room heat travel in waves. And what we're trying to do is that energy or heat transfer either gets transmitted through, it gets absorbed into the glass, or it gets reflected off. And we're trying to manipulate that to make the window a better insulator. So we might reduce our transmission a little bit by bumping up our absorption, or you bump up your reflection, but you're trying to reduce heat transmission through your window and make it a better insulator. And really, window design, there's loads of complexity that you can do to make the windows better performing. You can put shades in front. You can plant a tree in front of the building. You can have thermal broken edges. There's all these different things in terms of the window design. But in terms of the glass, the center of glass performance, there's really only a couple things that we can do to make the windows better performing. So if we use a darker, more absorbing glass, less heat gets transferred through. If we use a better gas in that cavity, if we go from air to argon or krypton, the larger the molecule is, the less things there are in there to do convection and conduction. So it just performs better if you have either better gas or no gas at all. A vacuum is a really good insulator. You can have a better performing low E. So when you talk about this, you a lot of times go from a hard coat to a single sputter silver to a double silver, or you can use more than one coating. You can put a coating on surface 2 and surface 4 in a window unit, or you can use more than 2 pieces of glass. You can go from a single glaze to a double glaze to a triple to a quad. But I mean, in terms of center glass, that's really it. That's all the triggers that we have to try to drive better energy performance for windows. So it's with those constraints and with the budgets and with the performance and aesthetic targets, we try to help people accomplish their goals. So what we see a lot of times is in new architectural design, it's not just simple, we want a green looking building that performs like this. We're trying to add different functionality. There's all sorts of different codes. Sometimes they're opposing codes that really the glass wants to do different things. So there are a number of things that architects and designers have to consider when they're looking at building design today. And sometimes that makes the glass and windows really complicated. So one of the things that we see was fire rated glass. This is becoming more and more common. The code typically says, this window or this wall has to resist a fire for 15 minutes, 20 minutes, 90 minutes sort of thing. And typically there's 2 different ways that we do this with glass components. So one is you get what's called a fire rated glass. So think of this as like your glass cooktop or Pyrex cookware or something like that. It's literally a ceramic glass that can withstand temperature for quite a while before that glass fails. So it's a nice product, but it doesn't always last for some of the higher targets required for fire glazing. So sometimes you have to have things that say, if that glass gets hit with a fire hose, it has to withstand the fire hose blasting at it for 15 minutes as well. Well, ceramic glass is going to shatter if it happens. So the other way that we do this a lot of times is typically 2 pieces of glass, and there's some sort of gel or goo in between them. And then that's what you're seeing in this picture here. Essentially what happens is the heat absorbs into that gel that's in the center, and it phase transforms from a liquid to a crystal. And that crystal transformation actually is absorbing the energy and withstanding and allowing you a longer amount of time before that unit will fail. So we see a lot of times fire resistant glazing is an important component. And really, I'm not an expert on this subject. We can point you to 3 or 4 people that can do, a dozen different hour-long seminars on fire resistant glazing. We're just trying to give a very high level review of the different products that customers might expect, or things that architects might consider. The other thing we see a lot of questions on, and this is becoming more important city by city and local ordinances now, at least in the US, is acoustic control. Like in New York City, the 5 boroughs all have different acoustic ordinances that they have to have for apartment buildings. And there's all this complexity that goes in. But acoustic control, in simply put, typically has the same sort of solutions. Sound travels in waves, and you typically need mass to absorb that wave. That's what most of these acoustic solutions have. So it's either thicker glass, it's lots of glass, it's a laminate in between, because the PVB or the interlayer material between the glass, that plastic material, absorbs that acoustic slightly different than the glass does. So there's acoustic PVB, really, really thick glass. VIG, or vacuum insulated glazing, is a really nice solution for acoustics because sound doesn't travel through a vacuum as well as heat doesn't travel through a vacuum. So that does a nice job knocking out your acoustics in a really thin form factor. Or if you take dissimilar glass thicknesses, a 6 millimeter over 6 millimeter in an IGU will not perform as well as a 4 millimeter over 8 millimeter in an IGU. And that's just because those 2 different thicknesses attenuate the sound slightly differently. So it gives you some benefits for it. But generally, acoustic solutions have one of those sort of kind of combinations of self-cleaning exterior glass. Again, it's not fully self-cleaning, but it 100% minimizes the maintenance that's required on the outside of the building. This is a really nice solution, and it's been around for about 20 years, but it hasn't really fully taken off. And I think one of the reasons why is if you put a self-cleaning glass on your number 1 surface, a lot of times that means you have to move your low E, which is typically on surface 2, to surface 3. So that drop off in performance, sometimes you can handle that and sometimes you can't. But we're now seeing double-sided products that you have self-cleaning glass on surface 1 and a low E on surface 2. I think this is going to really start to take off, because what self-cleaning glass does, and I'll explain the technology a little bit, but it typically is a UV charged coating that's on the first surface, that's on the outside of the building. And what happens is that coating gets charged, and then when any sort of bird fouling or any sort of organic material or dirt gets on that surface, the coating actually starts to break down that material. And then when you get rain, whether it's, or any sort of water, rain, a hose, it actually sheets the water off in a hydrophilic action. And it helps take that bird fouling or any material that's organic on there. Once it's broken down, it actually eliminates it. So the reasons this is nice and why architects like it is it minimizes the amount of cleaning, and it improves the aesthetics of what that building looks like month over month, year after year. So, maybe you reduce your building cleaning time from 2 or 3 times a year to 1 time a year, something like that. So it does have really, really nice benefits in terms of health of occupants. You don't have to send people up, and it reduces costs for a lot of building owners as well. Anti-reflective coatings, this is something else that we often see in design. And what we see with anti-reflective coatings is a single piece of clear glass has about 8% reflection. So each surface gets 4% reflection off of it. So when you take and put that into an IGU, you've got 4, 4, 4, 4, 16% reflectivity off of a regular window in a commercial building. So what we do is we put an anti-reflective coating on one of those surfaces, and that coating reduces your reflection from 4% down to about 0.7%. So if you laminate that together, you go from about an 8% reflection down to less than 1.5. So it dramatically reduces the reflection, and it gets rid of the signal to noise of what you're seeing through the glass versus what you're seeing reflected off the glass. And these are 2 examples of where this really manifests and it shows benefits. So one is in signage or display. So this could be in digital to signage or print ads. And it could also just be storefronts where people are wanting to see what's behind there. So we're seeing this a lot of time get spec'd in car showrooms and museums and places like that, where there's signage that's in there that we really want people to read and see what's in there. The other is in the vision areas. This is a great example of a stadium in North America, but this is the vision area. These are all the press boxes. And what happened with this one box in the middle that looks like it's kind of this creamy white color, I mean, that's actually kind of what normal reflectivity on glass looks like. Instead of putting the coatings on the outside surfaces, the fabricator just flipped them around and inadvertently put it against the middle. So all these areas around it have anti-reflective on both surfaces. You can see inside the overhead lights, you can see chairs, you can really see through the glass and into the glass. And where this really benefits is the people that are in the press box. When you're watching a game, you don't see that reflection of your high-vis shirt or the white lights behind you. You can actually see the sporting event. So there's really lots of nice benefits in your vision areas. And this was at the same stadium, same fabrication mess up. They even did it in the spandrel area. So instead of having that reflection of the glass onto the field where it might blind the players, they actually put it and flipped it around so you wouldn't get that glare down. And these are ones that, again, they just flipped around and you see the same reflectivity on it. But these are really nice ways that you can actually use anti-reflective coatings in your design to dramatically improve the look and aesthetics. Bird-friendly glazing. This is another kind of emerging topic. It's been around in discussion for maybe 5 years. It's not ubiquitous yet. It's not everywhere. But what people are seeing, at least in North America, there are a massive amount of birds. I think the estimate is between 100 million and 1 billion birds per year die flying into buildings. And people say, well, birds just don't see the glass, and people do. That's not true. People actually don't see glass either. What people see is context. Is you and I notice the framing on the door. We notice the butt joint. We notice the seams. We notice the handle. So therefore, we don't walk into the glass. But if you go to larger and larger pieces of glass and lower iron, where it's higher light transmission, what's becoming more common is people actually walking into these large sheets of glass. Apple built the spaceship in Cupertino, and they put in these massive low iron, clear, big sheets of glass. And within a couple of weeks, they had, I think, 3 or 4 people that broke their noses walking in to the window. So they had to like put stickers all along there so people would stop doing it. People don't see glass either. They see context. And so what we're trying to do with birds is, you can't educate them on context. What you have to do is put that context into the glass. And what's generally accepted is 2 inches by 4 inches. Every 2 inches by 4 inches, you have to put in some sort of contrast that gives them that big difference between transmission and reflection that says, hey, there's something here. And the majority, 99% of what's actually been done is people just put frit, little ceramic dots all over the glass. And that gives the birds context, and they can see that there's something there, and they don't fly into the glass. But aesthetically, that doesn't look great. You see all these little dots when you're looking through it. From the outside, maybe it's not obvious, but from the inside, you definitely notice this in your vision area. So what people are developing is these products based on the bird's eye. The bird's eye has this big spike in the UV where the human eye does not. So ideally, if you could put all that contrast in the UV, ideally you then make something that birds can really see and isn't noticeable to people. So that's what we're trying to develop. There's a number of people that are developing these enhanced coatings as well. And here's an example of one. This was done at the Calgary Zoo. And you can see in the top left here some of these lines, but there are areas that have in the UV very reflective UV and very highly transmissive in the UV. So when you get that context right next to each other, the birds can see that contrast and say, oh, there's something here. In the US, this is still very, very regional. There's no ASTM standard on it. Even the world's experts really don't agree with how are we going to test and do this. What we're trying to do as an industry is say, here's the way you test this. And if you test against these standards, you'll come up with a number that's a threat level, and anything better than this threat level will pass. That's what's trying to be done, but it's still kind of new and emerging, and it's really regional. So in cities like Toronto, in Minneapolis, in cities that there's a large migratory flight pattern that have a bunch of big buildings, there's a load of regulation on these things. Other cities, you might not even hear about this. So now I'm going to talk a little bit about emerging technologies. What I mean on this is it's not necessarily something that's brand new, but it is something that's starting to emerge as a bigger need and demand in the marketplace. So the reasons that we're seeing this is in North America, there's some performance targets that are out there that basically exceed what we're capable of achieving with the given technology today. So we make double glazing with one coating of low E. And if you look at the targets 5 years, 10 years from now, basically we can't hit those targets with the designs of stuff that we do today. We also see that buildings have very different demands today than they did 50 or 100 years ago. So you used to build a factory. That factory was to make whatever, and that's all it was. And now a building might get built that is mixed use. On the first floor, it's this building. On the second floor, it's something else. On the third floor, it's something completely different. And even on the first floor, maybe it's like a WeWork building or something else like that, where it's this type of building in the morning. It's a yoga studio in the morning, and then it's office space in the afternoon, and the demands and the needs of those different users are very different. There's also new technology available that wasn't available 50 years ago. And lastly, we're seeing cities have this holistic view to how they approach energy and building usage. And all of those things are driving these higher and higher, tougher demands that we just need to figure out, are there new technologies that maybe are a better fit to accomplish some of these new targets that we're trying to achieve? So the first thing on this is vacuum insulated glazing. And this, again, is not new technology. The first patents on this came out in 1913, where somebody just said, if I had an IGU and I just pulled a vacuum on it, a vacuum's a really good insulator, that'd be great. Well, the challenge is, if you do that, the panes will suck together, the glass will probably break, the edge seal is going to suck in, and then you're going to short circuit any of that insulation benefit because of that, that vacuum pressure. So it took almost 100 years. 1997 was the first commercial product that was available, and it's been around for 25 years now as a result, so 23 years. But the science behind this is, it's two pieces of glass. There's really three tricks to making a VIG product compared to an IGU. The first is what I mentioned, is that pressure. It's 0.1 pascals of pressure. That's about 1 ton per square foot. So the first thing you have to have is this microspacer array that keeps the panes from collapsing once they're put under pressure. So it's this little tiny metallic or some sort of hard compressive material. There's glass and ceramics and all sorts of different ones that are used. But you have to have something that's literally every inch across, or inch and a half across that entire face to keep the panes from collapsing under pressure. The next thing is you have to have a seal around the edge that won't suck in. So most times this is a rigid seal, so it's like a molten glass, low temperature molten frit, or it could be like a metal weld that you're literally welding the edge shut. And then the third trick to making that technology work is you've got to figure out how to get the air out. So most of this is done with, you drill a hole, you vacuum out the air, and then you seal that with one of those rigid materials. There are some materials out there that don't have that pump out tube. They're done in a vacuum chamber. There's a few other ones, but generally speaking, what's commercially available as a spacer array, it's sealed most times with a low temperature molten glass frit, and then there's a pump out tube to get the air out. But those are the three tricks on how to make the VIG design. But the reason this is really nice and interesting is it makes a really, really nice, highly insulated, better than the equivalent in an IGU, a really highly insulated product in a very thin form factor. So in 6 millimeters and a 1/4 inch thick, you can get down to about a 0.18 or an R5 insulator. And if you go up a little bit thicker, 10 millimeters or 3/8 of an inch thick, you can get up to an R8 product in a really, really thin profile. So that's really nice. The main reasons that we see this taking off instead of just replacing IGU technology is that thin profile really helps you maintain historic design. So a lot of times this is used in retrofitting existing buildings, adaptive reuse. If you have to reduce your energy bill and you want to keep your existing windows, or you want to keep the existing design from a heritage standpoint, VIG gets used for a lot of those sort of things. There are times where we see VIG get implemented because of the acoustic benefits, or because it's the weight. It's not that you can't handle the added performance of the added thickness. You can't handle the added weight of putting an adaptive reuse of a standard, say, 1 or 1.5 inch IGU. So we see a lot of wide varieties where this sort of technology is starting to take off. And then for, say a normal replacement window that you can handle an IGU, what we're seeing is people using that VIG pane as a hybrid VIG IGU. Now you have a triple glazed product in a double glazed form factor. That kind of opens up all sorts of different design criteria for you. Another thing that we see get used a lot is electrically conductive glazing. So this feeds into 24 different sorts of technology. But if you think about a piece of glass that's got a transparent coating on it, that coating then becomes the wire that drives a variety of different technologies. So this has been around for 30 years. It's actually been around since the 1940s, and it was used in World War II to heat vehicles. So I mean, it's been around for a while, but really commercially viable. It's been around for about 30 years, primarily in the commercial refrigeration market. So if you go in your grocery store, all we're doing is we're using that coating to heat up the glass 2 or 3 degrees, just so the windows don't fog up and frost up. So people that are in the grocery stores can see the labels, can see the signs, and they buy more stuff. That's the reason grocery stores do that. So that technology has been around for quite a while. But what we're starting to see people do is use this wire to drive new technologies and different technology. So these two pictures are of the same building. This is one of our customers that's over in Asia. And what they do is in a piece of glass, they embed RGB LEDs. So colored LEDs every inch. And then you have a computer that runs those, and the power to those LEDs is etched into the coating. And you run these through a computer program, and essentially then the building becomes a display. You could show movies on the building. You can have your company logo on the building. So these sort of technologies are really interesting in what it can do, and this merging of the facade and the display all into one really seems to be taking off. So that's one kind of thing you can do. But these coatings, again, they're enabling things like thermochromic paints and electroluminescent paints, where you need a current to drive that glow or that color of the painting. You know, it really drives a number of different technologies. We also see this used in touch screens. So if you just took a touch screen and you etched a grid into it, you can use that touch point to say, where is that XY, and use it for touch sensing. And then one of the latest things is switchable technology. So there's a couple different ones. There's thermochromic and electrochromic and a variety of different switchable technologies. And essentially what you're looking at on here is, if you see on the top and on the left, the glass is really high light transmission. And these panes in the middle here are kind of darker. So essentially what you do is electrochromic glass is two pieces of our glass. And think of it as the anode and the cathode of the battery. And then what's in between that anode and cathode, sometimes it's a gel, sometimes it's a solid state material, but by applying a current, you actually change the orientation of those cells in between, and you can darken up the glass, or you can lighten it up, or you can make it go opaque. You can do a variety of things. And this does improve building performance. I mean, it darkens the glass, it makes the sun's energy comes in less, so you reduce your AC bill. But the real benefit in electrochromic glazing has nothing to do with that. Is if you have windows that don't have all this glare, that don't have all this heat, you can actually sell that space better. And one place that this is really evident is in places like airports. We have a couple customers that, in some airports you go in, gate 6, it's unbearable to sit anywhere near the window in the afternoon because it's just too hot. So by putting in this switchable glass, you can actually tint it down and darken it to the point where it's comfortable to sit there. You can work on your laptop, you can see the screen. And what they're noticing is it opens up floor space of usable area within your building. It makes your comfort level and occupant level much, much better. And then they see other things like, well, the food court that's right next to that gate now gets more business. So now you can charge more for the rents in the food court. And there's all these kind of trickle down effects that really are the main drivers for these sort of technologies. So we see this as really starting to take off, and there's going to be a lot of interesting growth in this area. But again, it's managing light, and it's managing heat, and it's managing all these performance levels. Sometimes it can get complicated because it is now, instead of just having a passive product, you have an active product. And if you want to really make it work, you've got to tie it in with sensors, you've got to tie it into the building controls. So sometimes there does add some complexity in, and that's really what the industry is trying to figure out now, is how do we make all these things work. One thing I'll talk briefly on is pyrolytic coatings. So these are hard coats versus what's called a soft coat or a sputter coat. And you see both of these get used really in new construction, but there may be times that hard coat really makes more sense to get used. And the value proposition is just better with those hard coats. And one of the areas that we see this in is in terms of blinds versus daylighting. So what we'll see sometimes is people will design a building with really, really massive, 70, 78%, 72% high daylight products. And then the building is too bright, too hot, and you end up having to put in custom blinds, or you get this kind of sawtooth effect, or when people close this blind in this room and the one next to it doesn't look right. So you have all these kind of varying looks on the building as a result of your blinds. And you don't really a lot of times get the benefits of daylighting when people are closing your blinds. So if you design a building with a pyrolytic coating that's a little bit darker, you can get similar performance levels, but without all the variability in terms of aesthetics and performance that sometimes these blinds and high daylight products get. Another driver for why people a lot of times will spec pyrolytic glass is the supply chain. So when we make hard coats or pyrolytic coatings, you can make a bronze glass or a green glass, and you put this coating on, you could put it in the warehouse for 5 years and it has no shelf life. Sputter coats are these high performance soft coats. When you want to make that on a dark glass, we might only make bronze once a year. So you have to wait until we're on bronze, then we make the coating, and you have to make that coating on the substrate within about 30 days. And then you have to make that into a finished IGU within about 30 days. So if you're designing a high performance building with a tinted substrate, your window to make that building and get the glass might be once a year. So it really limits, the other parts of the project that you maybe didn't consider. The other area that we see this get used a lot is in lamination. So what we'll see a lot of times is these high performance low E's get laminated and put against the PVB. They can't be on an exposed surface that's out in the environment because they just won't handle the contact, the exposure to the environment. They get oxidized. So that's a really nice SHGC performance, but you don't get any U factor benefit. You don't get any insulation benefit when you take that and embed it against a PVB. So if you're going to have a lamination in your design, and this happens in areas like Florida where we have hurricane codes and things, is if you design in and have your low E that's on an exposed surface, you get the SHGC benefit and you get the U factor insulation benefit. So there's times that you may really want to consider, what do I want to spec into the building? And one of the other things I'll talk about, this is still new, is building integrated photovoltaic. So this is, instead of the windows rejecting the heat, reflecting it or absorbing it, or transmitting it, what you're actually doing is converting that from heat into electricity. So these are making PV cells into your transparent windows. The reason this is really interesting has to do with what's called ZNE or ZNC, zero net energy or zero net carbon. So what's happening is when you try to get your operating bill down to zero, you need to offset the amount of electricity that you generate by creating electricity. And in most small buildings, you can put some PV cells on the roof, you can put it in the parking lot, and you can generate enough electricity to offset your AC and your elevator and electrical use. But in really tall buildings, you run out of space. You just aren't generating enough electricity. So you start putting it in your spandrel, your transom, and your canopies and other areas, and you run out of non-vision area places to generate power. So you get to the point on these really tall buildings, the only way to get to zero net energy is you have to start generating electricity in your vision areas of the windows. And there's a lot of area of windows to start doing this. So we're starting to see this as a neat technology that's taken off. And there's a couple different products on the market today. A lot of them are either a combination of crystal and silica or different types of materials, but essentially what most of them look like is you embed that into a laminate and it's in the vision area, and most times you can see it and it has some sort of an aesthetic view. So this is one, it kind of looks like mini blinds. It's literally crystal and silica strips that are cut in and laminated, so it looks like mini blinds. So aesthetically, it's not a horrible looking product, and it performs pretty well. But what people are trying to do is get this to where it's not something that is a vision impacted product, and it's fully transparent. And there's a half a dozen different companies around the world that are trying to make these products today. And this is the sort of thing that you're actually looking at. These aren't going to perform as efficiently as a regular PV cell or crystal and silicon solar cell. So they might perform, say, half as well. But you have such a large area, and it's heat that you would be rejecting anyway, and now you're starting to actually generate that into electricity. So to me, these sort of technologies are really exciting in how that impacts the way that you start thinking about buildings and operations in the future. I'll talk very briefly on green building. This is most times what's considered LEED, or ways that you get credits in your building design. But what we're looking at here is there's a new code that came out in 2013. And again, I'm not an expert in any one of these subjects, LEED especially, but I can at least say in generality, here's the things that are going to get you LEED credits, and I can get you in contact with people in our company that really have much greater experience than I do. But there's a couple things that involve windows and glass when you look at LEED credits. One is reducing your fossil fuel, increasing your renewables, make the windows more energy efficient. So that's high performance, adding BIPV, making PV cells on your rooftops and in your transom areas, and putting dynamic glazing in. All these are things that can get you LEED credits. Materials and resources, there used to be a really convoluted calculation you had to do on how far was the glass made from where it was used and where's it going to get installed. And now it all comes down to EPD or environmental product declarations. So you have glass in your building, you get an EPD for it, you get enough EPDs, you can get LEED credits. And the last one is indoor environmental quality. So how much daylight, how comfortable it is, occupant wellness, all those sort of things are really the ways that you can drive credits. And then one of the last things I want to talk about is retrofitting. we're seeing this really large case for retrofitting being a much more interesting and valuable proposition from what it's ever been in the past. So when we think about existing buildings, most people don't include that when they look at construction or energy codes. Most times what we're looking at is the energy codes on new windows, or if you do replace the windows, they have to be to a certain level. But there's really been no emphasis on what do you do about all the existing buildings. But there's things in the US looking at, it's like called Architecture 2030. And in New York City, there's two laws, Local Law 87 and Local Law 97. So what these are now starting to do is say, any building that's bigger than either 25 or 50,000 square foot, you have to start doing an energy reporting every year. And then by the year 2030, you have to reduce your energy usage by 40%. And if you don't, we're going to start fining you. And if you look at 2050, that says we're going to reduce it by 80%. And if you look in more depth, in 2050, 90% of the buildings that are going to be in New York City in 2050 are already built today. So if we're going to solve these problems, we have to start addressing existing buildings and get them much more energy efficient than they are. And this realization is starting to cause this awakening where people are looking at how do we deal with existing buildings. And there's two tacks that people typically take when you have an existing building. So one is I want to keep the windows. Sometimes it's because I have to. It's a historically registered building, or I like the way that they look, but I want to improve the energy efficiency. So you do a secondary glazing, you do an interior exterior storm. That helps the energy efficiency, but it's not great. There are trade-offs in terms of aesthetics. You have to take them off and clean them. It takes up some space in your window framing as well. So that does a pretty nice job, but it most times doesn't get you all the way to energy efficiency of replacement windows, or you replace the windows. And in the US, 98% of the windows that get replaced are going to be using a double glazed window, a double glazed IG, and most times that has a low E on it. But when you do that, you rip out the original windows, so you lose all that heritage material, you lose all the aesthetics a lot of times of what that window looks like. You also typically have to put in something that's wider, thicker, and heavier than what you had in place. So sometimes you have to then beef up your framing to actually hold all this extra weight on the skin, and sometimes you actually lose some of your square footage of your apartments and that sort of thing. So that's typically what's been done, and what we're seeing people start to do is different approaches. So one of the things that we're seeing is, again, not new technology, it's just a new approach. And this may not be your every product or every case study that we do, but it might work in some cases. So we see people starting to reglaze existing buildings using vacuum insulated glazing. Again, you take out 1/4-inch plate glass, you put in a 1/4-inch VIG unit in that same space, huge energy efficiency improvements, and it doesn't really change the aesthetics of that original building. We're also seeing people start to address not the performance side, but the weight side. So what you see on the bottom right here is this is a storm window. And instead of being a traditional 1/4-inch or 6 mil piece of glass, this is a piece of 1.3 mil with a safety film applied to it. So this is going into large fixed building windows where people are pretty far away from the windows. But the reason they're doing this isn't to get a better performance than what storms do. It's to get that same performance, but without add all the weight. And then lastly, what we see people doing is using VIG as your storm window. Essentially, what you then get is a triple glazed performance in a retrofit solution. So you have the original window and you're putting in 2 pieces of glass in the VIG. So you get some really, really nice performance values with the still sort of the same way that we approach, this keep and retrofit treatment of secondary glazing. We're also seeing people start to address new ways to think about double glaze, and this could be like an old failing 1970s double glazed curtain wall, or it can be new construction that has a double glazing. But we're seeing people start to adopt what's called a thin triple. So if you imagine a 1-inch IGU, and instead of going to an 1.5 inch triple glaze, all this does is it takes a piece of 1 millimeter, really thin glass, puts it in the middle, and then it is a Krypton fill on both sides. Now what you get is triple glaze performance and a double glaze form factor. So whether you're retrofitting an existing double glazed curtain wall, or whether you're putting this into a new construction that's used to handling 1-inch IGU, you're getting that performance without sacrificing your form factor. And you can also do this with what's called a hybrid VIG IGU. So that same double glaze, you use one of the panes of glass as a VIG. And then lastly, again, addressing the weight side versus the performance side, but using thin glass as your laminates instead of doing 1/4 inch over 1/4 inch or 3 mil over 3 mil, if you can use a thin piece of glass for that laminate, sometimes you can get really similar performance values, but not add all the weight to the design. And again, really, really nice performance levels. So last thing I'm going to talk about is a couple of case studies where some of these retrofit solutions happen. One of the biggest ones, this was a building in Milwaukee, an Aero Saarinen design building, who's a famous architect. This was designed in the 1950s, 1955 construction. And the architects were hired to do a curtain wall replacement. So they were going to just re-curtain wall the entire thing. And they said, well, we can do that, but it changes the design of Saarinen so much that let's look and see, can we actually maintain this? And when in fact they went and looked at it, the steel was in really good shape, so they could have been able to save it and just clean up some of the corrosion and things like that. So they looked at their glazing alternatives, and what they said was it was 1/4-inch wire glass that was in place, and there wasn't really a good monolithic solution, like a low-E hard coat that really hit the performance values that they wanted. This is the main staircase between the 4 levels of the museum. It's a historic heritage national register building, so they wanted to keep that design if at all possible, but it just couldn't get them the performance and comfort level that they wanted with a single low-E coating. And they could have put in a 1-inch IGU and just move these glazing bars back, and it really wouldn't have changed the aesthetics of what that building looked like. Really would have looked okay. You wouldn't have impacted your sight lines, but it would have meant they would have had to reglaze 14,000 glazing bars, add tons of new holes, refill the old holes. It would have added about 2 months to the glazing schedule. And the project cost overruns just made it to the point where it didn't make any sense. So they ended up reglazing with VIG. They used the same glazing bars, the same holes, the same screws. And it was actually the lowest cost alternative product. And it worked well, and it kept Saarinen's design. So this won a few federal and state AIA awards. And again, it's one of those things that it may not be the solution for every project, but there's going to be projects that this might be the best fit you can have. And then a similar story was this is in Winston-Salem, the Union train station. So again, this was built in 1926. They're going to make this into a museum and mixed-use offices. They had to improve the energy efficiency, and in this case, what they were going to do is add interior storms to get the energy efficiency up. But they had these beautiful old, they're steel casement windows, bronze hardware, I mean, gorgeous. But what happened with interior storms is it changes the sight lines enough that it messes with your views. It covers up all these beautiful bronze hardware. It adds a couple inches, it adds maintenance, and it doesn't really get to the energy efficiency that you want. So by reglazing with VIG, they were able to keep the aesthetics of the original building. And it ended up being a beautiful project. I mean, it looked exactly like the original building. When you walk up from the outside, it looks like plate glass. But it got them the performance that they wanted without the other design trade-offs. So that's the conclusion. Again, hopefully this has been interesting. If you have any questions, I am always open to discussing projects, giving advice. I tell people that I'm a glass guy, so we make glass for all these different solutions. We're kind of technology agnostic. So if you have an existing building, we may not even make a product that's a good fit for you. But if we can say, well, you might be better off with a storm or a VAG or a IGU or a triple glaze, any sort of problems that you're coming across, we just try to look at different ways of using glass and glazing technology to help you solve your problems. So if you ever have any questions, you're up for a question or need some advice, please feel free to reach out anytime. Thanks again for your time, and I hope you have a great one.